Life isn't always a smooth ride. There will always be resistance along the way, and so does a flowing water. Aside from its internal friction as water pass by each other when it is flowing, there will also be some other factors externally. So, around the perimeter of the walls or the boundaries where the water is flowing, it may it it would be it may be a pipe, it could be a channel, diba? Around those perimeters, it offers resistance. And so that's where boundary shear stress kicks in. All right? So basically, shear stress is a stress that is always tangent to a given surface. Diba? It is the resistance offered by the walls of any channels where there is a flowing fluid. So if we zoom in to this kind of topic, we will see that in this particular part of the channel where there is a flowing water, these boundaries, the upper and the lower, or kung napakas above ani galantaw and this is your channel, the sides, diba? Will offer friction or resistance to your flowing water. So, in order for us, since this topic is all about designing a channel, and I guess one factor that is very important is this boundary shear. Because knowing such will lead us to decide, will give us a guide on how to decide our channel, di ba? Saan na to pag-design ng atong channel if given these parameters and data. So of course, it will start with knowing the velocity profile. Because if we know the velocity of that moving water, then we'll know how much force will that water exert to the sides of the channel, di ba? Okay, what if that is very strong? The velocity is very fast. This moving water is very fast. Then it will give much stronger wear and tear to the boundaries of your channels. And as a designer, you don't want a channel that is that will easily get dali lang maanod or maguba sa imuhang flowing water, diba? So you'll design some stronger. And so that's why boundary shear stress is important. Diba? So what is a shear stress? So imagine having a block of force. This is the water flowing. This in the right side, muna siya na strain, diba? Tungod sa flowing water. So imagine if that is the wall of your the boundary or the wall of your channel, the pipe ba or open channel. If kana is the strain, then that wouldn't be a good sign for you for your design. So if this is your boundary, if that is the wall, and this is the water flowing through it, diba? So that is shear stress. Kini nga force in the blue, this one, is the tangential force and somewhat like slicing your boundaries or the walls. Mo na ang element sa water, diba? And due to the Newton's third law, action and reaction. So when your water strains like this and there is a cohesion or friction happening, resistance happening from the strip or in very gamay nga strip sa wall and the water, mo siya may tabo na ay shear stress. So why is knowing shear force and shear stress or the boundary shear stress itself important? So as what I've said, it is important because in your channel, it will of course undergo wear and tear. Diba? And then, magkadugay ang imong channel, ang atong aim is dapat mulas siya aglong and then ligon pod ang atong channel. So that's why important ang may bala nato ang boundary shear stress and how strong ang stress diya para maka-design ta og mas ligon, di ba? Mo man atong goal good. Shear force is the force that is always tangential to a given area. So, di ba? It gives a kind of slicing failure to whichever surface it is present on. Mura siya og kutsilyo and a cake. When you are slicing a cake, you're putting shear stress on that cake. Diba? That's the analogy here on what is shear stress. Now, since force is always applied to a finite area no matter how small it is, diba? Imagine, dagom. Bisan pa balin ang gamaya na nga dagom, as long as naa na siya area, microscopic area pa man na na siya stress gyud matawag ana because it is applied to an area, di ba? Kung tanawon ninyo ang formula siya sa shear stress, di ba? Force over area ra mga gapon. Kanus aman may tabo nga mahimong A equals 0. And when it happens, di ba? If A equals 0, that would become unsa may tabo. In mathematics, that's a no-no rule, di ba? Di na may tabo. It will become, say, tawagan na nila, undefined, di ba? Undefined. May mga undefined. So, there is no undefined force. Good. So, no matter how small it is in stress quantity, good na. Ang shear. So, mo nang gitawag nilang shear stress, dili shear force because it is applied on an area, no matter how small it is. No matter how infinitesimally small ba na siya. Alright? Alright. So, muna siya. Since force is always applied to a finite area, no matter how small it is, shear force can be analyzed as stress. Water flowing in a channel also experiences this stress, and that's where boundary shear stress becomes a great factor when you are designing. Muna ito, as what I have said a while ago, ang shear stress, importante gula nato nga mahibalan. So, we could design from it. Diba? Mo decide ta based sa data nga atong makuha. Diba? Imagine this is your river, no? An open channel. And this is your flowing water. So, sa perimeter, gudana niya, kaninga channel. Sa side, sa bottom, na siya, yung resistance good. Di na may tabong wala. Na friction. And when there is a friction, and there is a cohesion happening between the water and the boundaries itself, pinigyuta na siya or concrete ba ang boundaries, na may tabong shear stress. Muna siya ipasabot sa boundary shear stress. Alright? When that is your open channel. And then, of course, if your channel is in the form triangular ba, then kining sides, dire, muna siya mo undergo shear stress. Maka-experience shear stress diya. And then, the next question is, how do we quantify this boundary shear stress? Now that we know unsa ng shear stress, unsa ng boundary shear stress, ang next na po natong i-ask sa atong selves kay how to quantify boundary shear stress. There are several devices that can be used to quantify shear force and its relation to flowing fluids properties. Diba, ang flowing fluid, nagana siya properties. Could be its viscosity, another factor, temperature, and so on. Diba? Velocity, pressure, viscosity, maka-apekto yun na siya sa shear stress. And pitot tube is one of them. Diba? Pitot tube. This device helps measure how fast a fluid is flowing in a channel. Since velocity is an important factor for us to know what is boundary shear stress, and we want to know how to quantify, pitot tube is the answer. Pitot tube is a device that quantify or iyang sulbon ang velocity sa flowing fluid. But how? Saan niya? Diba? Muna yung next na itong pangutana. But wait, ako sa basaw na. It is important because faster flowing fluid might cause large shear stress on the wall boundaries of a channel, and so it can be used as a guide in design. So, kato siya may mo-govern. Kung madako ang shear stress di adapita sa imuhang walls, sa imong channel, then that will govern your design. Now, going back, how does pitot tube measure velocity of a flowing fluid? So, imagine a pipe that has a flowing water inside it. Diba? Pipe lang yun. Nga ay flow nga water inside niya. Diba? Of course, kana nga water, it will occupy all the space inside. And so, iyahang maka-experience og shear stress ang tubig ug ang wall itself. Diha kay ang water, if once it flows, once mo flow gyud ang tubig, mamulong na siya ka-escapean. It will always find an escape para mo gawas gyud ang water. It will occupy the space man. So, bulong gyud na siya magawsan niya. So, no matter how small the hole, diba? Kung pangagan yung na diha, musirit gyud ang tubig diha, magawas. Now, moving on. Na ay gitawag na piezometer tube. So, piezometer tube measures the static pressure of the moving water. So, as what I have said, bisa pag unsa nakakuan yung tubig dira, di ba? Anang flow niya, kung bangagan na nimo, bisa usa kagamay na mamulong gyud nag-alagian ng tubig, whether paangat mo na siya or samot nagpalugsong ang imong bangag. So, inigsaka ani niya aning tubig dire sa hole due to this tube, piezometer tube ay lang tawag. Naatay mahitabo nga rise in waterhead. Ang kana nga waterhead nga ni rise, muna gitawag nila static pressure. Diba? Muna. water will always enter no matter how small a hole is. Kini nga ni rise nga water diri sa piezometer tube. That is what they call static pressure. So ang fluid nga na stock, of course static fluid. But ang measure from diri sa tube to the height sa water nga ni saka ni elevate is what they call static pressure. While the moving fluid is of course dynamic fluid. It is moving. Now, if the channel is completely horizontal, static pressure reading in piezometer will always be of the same level as well. Of course, kay kuan man sila. Kung mo na siyang islant gamay, isa ang diri sa right side, ma-change na po ang static pressure head. Alright. If horizontal, then they will be out of the same level. The tube now is inserted, and as expected, water will rush in. Sama itong pagbangag na to, and then we put the piezometer tube in this pitot tube. Of course, water will also rush in or will enter the pitot tube. Of course, masaka na siya, ma-rise yapon ang tubig inside niya. And naana po siya static pressure inside. The rising water just above the static pressure is now the dynamic pressure head. So not only that musaka ang tubig dire no sa atong pitot tube, mas musaka pa good siya compared sa piezometric. Kaya tanawon nito ang iyang setup, ang piezometric igo raman siyang nasa babaw, naraman siya hole. But ang kining pitot tube ato gid siyang gi-insert. Man ni collect di jag water, di ba? Kay atong gipa atubang sa flow gyud. Mo ni siyang nani siya dynamic pressure nga ni saka. Now, ang pangutana di ba, how will it measure? So since ang tubig mosulod man aning pitot tube, di ba? Naragunay limitation, naragunay point wherein dili na kayang mosulod ng tubig diri sa pitot tube because maglaban na mo fight na against each other ang tubig kining flowing fluid damagan niya ning weight sa kaning tubig nga naa sulod. So naragunay point nga mo stop nagsulod ang water, and that point kining nadire is what they call stagnation point. There will be a point where water will stop entering the pitot tube due to the flow and the weight of the water inside the tube fighting against each other. Ganahan mo gawas ning tubig nga naa sulod sa pitot tube, and ganing naas gawas ganahan pud mo sulod due to the flowing water. May siya silbi nahitabo diha. Alright, that is what I've said. This is what they call stagnation point. And of course, when there is a stagnation point, mo stop nag-enter ang water diri sa pitot tube, that is where the velocity becomes zero. Mo stop man ang flow diri nga point, stagnation point. So by applying Bernoulli's equation no diri sa point na where the flowing water is located and at the stagnation point, diyan na nato may bala ang velocity sa water, di ba? To derive the formula to find how fast the water is moving, we will just apply Bernoulli's equation to point 1 dira sa moving water. Anang yellow, makita ninyo yellow. And then that at stagnation point, which is point 2. Bernoulli's equation again is just the pressure plus the pressure head, and then 1/2 rho 1 b1 squared, another head measurement, and then equating it to the stagnation point. Then na-cancel ra ang heads, elevation heads, rho gh1 and rho gh2 because our water or our pipe is of the same level lang, diba? And then of course at stagnation point, V2 is equal to 0. Then by some sort of algebraic manipulation here, makakuha ta nga velocity of the moving fluid, diba? At point 1 is equal to the square root of twice the pressure difference over the density of the moving fluid. So kung water na, the density of water. Ano lang ang pag-find sa velocity of a flowing fluid. O, diba? Now, how can we apply this, knowing this? Ingani ra di ay no, gamit tag device nga pitot tube, then makuha na to ang velocity sa moving fluid. Nana ra di ay. Unsa na to pag-apply haron maibala na to ang shear stress, ang boundary shear stress. Simple lang. In reality, mo gamit tag daghan kaayong pitot tube. Mo undergo guna siya og daghan kaayong tests and experiments. And diha mabala na sa mga hydrologists ba ang velocity profile. And once we know the velocity profile with some sort of mathematical tools, may bala na to ang boundary shear stress. So later on I will show that to you.
When the United States sails from New York to London, the entire Atlantic Ocean is actually disturbed by the ship. Similarly, an airplane in flight disturbs all the Earth's atmosphere. Intuitively, however, we feel that only a small part of the ocean is important to the ship and a small part of the atmosphere to the plane. Here, a thin plate is towed longitudinally through a tank of very viscous liquid at slow speed. Observe that all of the particles in the field of view are set in motion, although with decreasing speeds far from the plate. Now the plate speed has been increased, yet the particles far from the plate no longer appear to move. Actually, they are moving at least as fast as in the previous scene, but the camera speed has been increased to prevent blurring the action near the plate. The lengths of the red lines are proportional to particle speed. It may be reasoned that there is some fluid particle speed, so slow compared to the plate speed that particle motions at slower speeds may be entirely neglected. This speed is usually taken as about 1% of the plate speed. If a bounding line is drawn to include the fluid particles whose speed is 1% or more of the plate speed, the region bounded by the line is called the boundary layer. You are now moving with the plate, so that the undisturbed fluid appears to be moving past the plate. The lengths of the red lines are still proportional to the relative fluid speed. The boundary layer is identical with the previous case, but it now has to be defined as the region within which the fluid speed is less than 99% of the apparent stream speed. The boundary layer grows thicker with distance from the leading edge. The growth rate is not linear, however. The boundary layer becomes thinner if the velocity is increased. If the viscosity is decreased, if the density is increased, or if their ratio, the kinematic viscosity, is decreased, the boundary layer also becomes thinner. When these factors influencing boundary layer thickness are combined, we find that the dimensionless boundary layer thickness, delta over x, depends inversely on the Reynolds number formed using the distance x from the leading edge as length parameter. By theoretical calculation, delta over x is approximately equal to 5 over the square root of Reynolds number. In air, boundary layer development is the same as in liquid at the same Reynolds number. Identical laws hold for all fluids, whether liquid or gas, at least as long as the fluids are incompressible. Boundary layer velocity profiles are produced by shear action between adjacent layers of fluid. The magnitude of the shear stress is given by Newton's law of viscosity. shear is eventually transferred to the plate surface, where it is felt as drag or skin friction. Theoretical calculation of dV by dy at plate surface permits evaluation of the wall shear stress at each x distance, and drag is obtained by integration over the plate of length L. Drag is conveniently expressed in terms of a dimensionless skin friction coefficient, C sub F, and this coefficient is a function of Reynolds number only. The flows we have been looking at are laminar flows, but laminar flows and their associated theoretical formulas cannot be extended to arbitrarily large Reynolds numbers. Rather, the boundary layer becomes thinner at a given x distance as the velocity is increased or as the viscosity is decreased. And the shear stress or friction at the wall increases until the boundary layer bursts into turbulence. Turbulent flow is characterized by random whirls or eddies as opposed to the smoothness of laminar flow. Turbulent, laminar. Watch the boundary layer become turbulent as the plate is towed past the camera. Again. The upper boundary layer in these pictures has been made turbulent by placing sandpaper on the plate surface to create a disturbance. The lower boundary layer is still undisturbed and laminar. Turbulence can be generated in the boundary layer by disturbances only if the X Reynolds number is greater than about 100,000, so that close to the leading edge, the boundary layer must always be laminar regardless of disturbances. A transition region of intermittent turbulence connects the laminar and turbulent portions of the boundary layer. Observe that the flow outside the boundary layer is undisturbed and laminar. But even if the outside flow were turbulent, a laminar boundary layer would originate near the leading edge, becoming turbulent later. Outside disturbances influence the location of transition. By carefully avoiding disturbances, transitions can be delayed to Reynolds numbers of several million. Here, a turbulent river flows over a dam. A boundary layer originates on the concrete surface at the top of the dam, becomes turbulent, and thickens until it reaches the water surface where it becomes visible, because the small, intense eddies of the boundary layer turbulence entrap air from the atmosphere. The original river turbulence is invisible because its eddies, which originated on the riverbed far upstream, have decayed. A turbulent boundary layer is thicker than a laminar boundary layer at the same Reynolds number, and velocity profiles are much flatter in the turbulent case. shear stress is no longer given by Newton's law of viscosity. Between the turbulent fluid and the plate, too close to be seen clearly in the picture, there is still a laminar sublayer in which shear stress can be calculated by Newton's law. Velocity gradients and shear are very large in the sublayer, so that the skin friction coefficient exceeds that for a laminar boundary layer at the same Reynolds number. Since the boundary layer near the leading edge of a plate is laminar all of the time, the integrated drag on the plate is made up partly of laminar and partly of turbulent friction after the boundary layer becomes turbulent. Because transition depends on the disturbances that are present, there may be more than one value of the skin friction coefficient for a given Reynolds number. However, when transition occurs near the leading edge of a long plate, friction of the laminar part is negligible compared to that of the turbulent part, and there is a unique relationship between skin friction coefficient and Reynolds number.
Knowing the velocity of upflowing water is only one ingredient in determining the shear stress in the boundaries of a channel where you are designing. In reality, a number of pitot tubes and several attempts and trials is done in order to attain a certain velocity profile. Diba? In summary, we need pitot tubes to know the velocity profile, and we need velocity profile of a flowing fluid to know how fast a water is flowing in a channel, how it behaves, and finally, use this data we've gathered to determine the shear stress in the boundaries where the flowing water is moving or in contact with. So mo tayo ang akong giingon nga if there is a flowing water, there will always be shear stress happening on the boundaries between the boundary and the flowing water. And for us to know what is the magnitude, how strong that shear stress is, kailangan tawag device, which is the pitot tube, to measure the velocity. And if we know the velocity, makagamit ang mathematical tools, makuha na ito ang relationship between the velocity and other factors, and of course, to the shear stress. Ano lang ilahang relationship among each other. So with this enough data from numerous successful experiments, it will finally give us a guide on how to design a channel. Bawa usara na siya factors in designing a samot drainage channel. Usara gyud ning boundary shear stress. And knowing such, mo to ang ingon na ay wear and tear, of course, because of friction, diha ta maka-decide na ta kung unsay atong gamiton nga materials for the walls sa atong channel, di ba? Or the roughness. Ano lang ang ilahang connection. So, to cap it all, para mabutang sa atong una-una, dali rang ma-remember and ma-relate ang tanan nga atong na-discuss, natay sample problem. So, again, diba, kuha na tag pitot tube to find the velocity. And then, sa atong kaninga sample problem, nigamit na sila og pitot tubes, and muni ang na-find out nilang velocity profile na daw in a form of parabolic. Diba? So, how can we relate this all? So, ato sa basaw ng problem. The velocity distribution for laminar flow between parallel plates is given by muni nga equation. So, parabolic siya. U over U max is equal to 1 minus closing quantity 2y over h squared. Muli, kaning equation is the velocity profile. Where U max, ang maximum daw nga velocity is equal to 0.30 meter per second. So kung makita ninyo, base lang po datong video, di ba? Ang maximum gyud nga velocity may tabo at somewhat center sa pipe. Diha ang maximum because diha ang walay resistance. Wala man diha dapit ang wall. Di ba? So somewhat intuitive lang pod nga ang dire gyud sa wall dapit ang mas hinay mo flow kay namay mo resist sa flow, di ba? Naman na siya. And then ang ipabuhat is compute the shear stress on the upper plate and give its direction. Patag daw ang direction. Given the properties of water. Water at 15 degrees Celsius and its dynamic viscosity dynamic viscosity mu na siya, is equal to 1.3 times 10 to the negative 3 kilograms over meter over second. And the height daw sa kaninga channel is just 0.5 millimeters. So that's a small quantity. Small depth lang siya. So how can we solve this? This is now the solution. So of course, to relate the shear stress to the velocity profile, we have the formula tau is equal to dynamic viscosity of the fluid multiplied by its velocity gradient. This is applicable for Newtonian fluids. Mani siyang may tabo. So, if i-follow ra nato ang formula, du over dy is just the velocity gradient. And we already have u if we rearrange the equation or the velocity profile. Diba? I-transpose ra nato ang u max, makakuha tag u which is equal to u max multiplied by that quantity inside the bracket. Mani siya. And then getting its derivative, the derivative of the velocity gradient will give us u max and that quantity inside the bracket. And then simplifying, makakuha tag velocity gradient which is equal to negative 8 times the u maximum, the velocity maximum velocity, times the depth, times the overall depth which is h squared. Kaning depth, kaning y, mo say mo tell nato kung asa dapit sa ato ang channel, no? So nantay coordinate axis y positive above and then x positive to the right. And then if we wanna know what is the shear stress on the upper portion, unsa may ato ang mahimong y. Ang y nato is just half, diba? H tibuok man nato ng 0.5. So half ana is the upper plate. Muna siya location. So 0.25 silbi ang ato ang kuan positive. If we wanna know the boundary shear stress below or at the bottom, of course atong gabito is negative 0.25. So ano lang, we already have the formula is tau is equal to dynamic viscosity times velocity gradient. Nanatay dynamic viscosity for water at 15 degrees Celsius which is 1.3 times 10 to the negative 3. We just have to substitute all values. Natay negative 8 and then maximum velocity is 0.30. And then we have y. We want to know the shear stress on the upper plate. So muna siyang 0.25. Then times 10 to the negative 3 because it is in millimeters and all this value must be in meters so that uniform ang ilahang units all over the overall height or depth sa ato ang channel which is 0.5. Of course in mm po na siya. To make it in meters, we just have to multiply it 10 to the negative 3. And we will get a value of shear stress which is negative 3.12 Newton over meter squared. So kana siya is not yet the answer because in deriving this formula tau is equal to mu du over dy, it refers to the fluid itself. So by the third law, following the third law of Newton, action-reaction, the final answer will be 3.12 which is positive. This is the stress that the walls of this particular example is experiencing. Mo na siya ang na-experience. 3.12 to the or against the shear stress of the water. So ano lang, that's how we quantify shear stress based on velocity profiles and Pitot tube and all of that. I hope you got something here. Thank you so much for your patience in listening and thank you so much and peace out.